In the last class, we looked at the pKa table, and we also said that we will use this pKa table to figure out the outcomes of organic chemistry reactions, right. So, now what we are going to do is we are going to use the pKa table to first predict the K equilibrium of any acid base reaction. So, now let us take a generic reaction. I am going to take HA plus B giving me BH plus A minus, right. So, this is a generic acid base reaction. Now, just to make you guys go back, we talked HA being the acid because it gives us a proton, B is the base, BH plus which is going to act as a conjugate acid, right, because if the reaction has to go back, it needs to function as an acid. So, I am going to say conjugate acid, and A minus which is going to function as the conjugate base, right. So, this is a generic reaction between acids and base to give you conjugate acid and conjugate bases. Now, the K equilibrium of this reaction we have said is equal to concentration of products over concentration of reactants, right. So, concentration of products. So, in the case of products, I have concentration of BH plus, concentration of A minus over reactants which were our acids and base, that is HA and B, right. Now, let us explore this equation a little further. What I am going to do is I am going to multiply this K equilibrium by 1. Okay. So, I am going to write KEQ into 1 is equal to concentration of BH plus, concentration of A minus over concentration of HA and concentration of base. Now, on the left hand side we multiplied by 1, on the right hand side also we are going to multiply by 1, but we are going to multiply it in this notation. So, we are multiplying and dividing by H3O plus, right. So, this term in all is 1, right. So, we are multiplying both sides by 1. Now, let us separate these terms a little bit. So, what I have here is concentration of A minus over HA, right, into concentration of H3O plus into concentration of BH plus over B and concentration of H3O plus, right. So, I have not done anything different, but I have just written these terms such that I have separated such that they make some sense. Now, if you look at this particular term, what does it remind you of? If you look closely, this particular term talks about the Ka of dissociation of an acid HA. How is that? Let us look at that. So, if I take HA plus H2O, wherein water acts as a base, that water is going to give you H3O plus A minus. And what will be the Ka of this particular reaction? So, Ka would be concentration of H3O plus, concentration of A minus over concentration of HA. Okay. Rather, if you want to go back and revise something that we saw in last class, KEQ will be concentration of products over concentration of reactants. So, that is it. But when we multiply KEQ by concentration of water, which is pretty much constant during the reaction, we get Ka. So, Ka will be concentration of H3O plus over into A minus over HA, right. So, this is Ka. This particular other term on the other side is actually the dissociation constant for an acid BH plus. So, which is exactly the same. So, I will not go through the details, but you can see BH plus H2O and you can figure it out yourself. giving you H3O plus plus B. So, this particular term here will be 1 over Kb, or rather KBH plus, right. So, our initial reaction, which was HA plus B giving you A minus plus BH plus, and the KEQ for that. So, the KEQ for that is nothing but the dissociation constant for HA divided by dissociation constant for BH plus, right. Now, let us take the pKa. So, pKaQ will be pKHA minus pKHB plus. I want to point out one thing, HA was our acid and BH plus was our conjugate acid as we started writing this reaction, right. So, what I have here is KEQ will be dissociation constant for the acid divided by the dissociation constant for the conjugate acid, right, in any acid base reaction. So, if I have to generalize, if I take the negative antilog of this particular reaction, right, because pKEQ will be minus log of KEQ to the base 10, right. So, now if we take the antilog, then what I have is KEQ will be 10 to the power conjugate acid pKa minus acid pKa, right. So, now we have this formula, or if you want to simply remember, KEQ will be 10 to the power pK on the right hand side minus the pK on the left hand side. And this is a very useful equation, because with this equation I can figure out the KEQ of any reaction, right. So, now let us look at couple of reactions of acids and bases. So, I am going to take a reaction here which is acetic acid and water, right. Now, as these two molecules react, you are going to form acetate and H3O plus, right. Let us figure out the KEQ for this particular reaction using the formula that we just derived. So, the KEQ for this reaction, first I need to figure out the acid and the conjugate acid. The acid here, the molecule that is losing the proton, is actually this one, which is our acetic acid, and the conjugate acid, which is going to lose a proton in the backward reaction, is going to be the H3O plus, right. So, in this case KEQ will be 10 to the power conjugate acid pK, which is minus 1 according to the pK chart, minus the acid pK, which is around 5, right. So, that is 10 to the power minus 6. So, that tells you why acetic acid is one of the weakest acids that we see around, right. Or why is it termed as a weak acid as compared to most of the mineral acids, HCl and H2SO4 or acids like that, right. Because if you see, if you take 10 to the power 6 molecules, only one of them probably gets dissociated as we add acetic acid and water together. It is very less dissociation happening, because acetic acid will stay as acetic acid and will not form that acetate ion, and thus it is termed as a weaker acid as compared to HCl, HNO3 and acids like that, right. Now, let us look at one more reaction. Now, I am going to take acetic acid, but instead of taking water I am going to take NaOH. Okay. NaOH, as we know, is a base which is nothing but Na plus and OH minus, right. There is the ionic bond between sodium and hydroxide. So, what I have here is, again this hydroxide is going to act as a base, it is going to go and grab this proton and then push these 2 electrons on that oxygen. So, also pay attention to the arrow pushing, because that is one of the most important things to know in an organic chemistry class. So, the next thing is it forms water. Now, let us look at the KEQ for the reaction. I have acid which has a pK of 5. I have the conjugate acid. Now, instead of H3O plus, the conjugate acid now is water. So, in the case of H3O plus, you had a pK close to -1. In the case of water, the pK is close to 16. So, the KEQ in this case will be 10 to the power right hand side pKa, which is 16 minus 5, that is 10 to the power 11. Okay. So, now you can see why acetic acid and base like NaOH will react vigorously to form that acetate ion, but the water molecule will not really dissociate acetic acid into acetate ions. So, this clearly tells me one of them has a K equilibrium of 10 raised to power minus 6, meaning the concentration of products is very small, right. 10 raised to power minus 6 is a very small number. Whereas, in the case of the later reaction, the concentration of products over reactants is 10 to the power 11. So, 10 to the power 11, it is really large number. So, you can see why acetic acid reacts with 2 different compounds H2O and NaOH differently. Now, let us take one more example. I have an acetylene molecule and I want to use NaOH in order to deprotonate it, okay, right. Again arrow pushing, this attacks here. So, I have HC triple bond C minus plus H2O. Let us figure out the acids. So, this is the acid because it is losing the proton, and this is our conjugate acid, right. Now, if we take the KEQ, which is 10 to the power conjugate acid minus acid. So, it will be 16 minus the pKa of acetylene according to your pKa chart is close to minus 25, right. So, this is close to 10 to the power minus 9, right. So, the KEQ for this particular reaction is 10 to the power minus 9. One of the questions people ask is that since it is an equilibrium, does it mean like if I let these 2 compounds sit together for a long time, eventually the system will reach equilibrium and such that the reactants and the products will have equal concentration. So, that is one of the questions more often asked, right. The other question that is more often asked is, what about the starting concentrations of the reactant? So, like if I take a really concentrated NaOH, will it eventually make the reaction go in the forward direction? Currently understand that the KEQ is 10 raised to power minus 9, which is concentration of products over reactants, again meaning that you will not form that anion that we have shown, right, because concentration of the anion is very negligible, right. So, let us go back to the 2 questions. The first question was, what about the does it mean that if I let these 2 sit together, will it eventually lead to the equilibrium, meaning 50-50 concentration? One of the things I want to point out here is that equilibrium does not necessarily mean that a 50% product and a 50% reactant are formed. We have seen such reactions before wherein equilibrium meaning both the things are equal. When we assume a 50-50 distribution of concentration and products, we are assuming that they are equally stable, meaning the products are equally stable and the reactants are equally stable, and then we can assume that as the reaction happens, eventually it will lead to equal formation of reactants and products. In most of the acid base reactions, you will see is that the stability of the product depends on the stability of the conjugate base that is formed. So, in this case, this particular conjugate base that is formed will govern the stability of the products totally. Now, what you observe is that more often in acid base reactions, the stability of the products and the reactants is not the same, as a result of which it is wrong to assume a 50-50 distribution at equilibrium. When I am talking about equilibrium, let me go over the kind of equilibrium that I am referring to in the case of acid and base reaction. Now, to give you an example of the kind of equilibrium that we are talking about, I am going to use an analogy, right. So, I am going to take a water tank on this side and another water tank on the other side, which are basically which have a gate in between, right. And then what we are going to do is, we are going to have some fishes, right. So, let us say that we start from 4 fish here, and then at the beginning of the experiment there are no fishes on the right hand side tank. Now, as we open this gate, what is going to happen? Eventually the fish are going to travel to the right hand side, some of them will travel back and forth, back and forth. Eventually at equilibrium you may find a situation wherein there are 2 fish here and the other 2 fish are in this particular other tank. Now, again we are talking about fishes, not really chemical molecules, but just imagine this as an analogy. So, the equilibrium, the kind of equilibrium that we talked about previously was that 50-50, meaning 2 here and the other 2 in the other tank. Now, imagine a situation wherein you have the same fish tank, right, but now you have a cat sitting on one of the sides, which is ready to eat these fishes, right. So, this particular cat, you think the fishes will travel close to the cat? The answer would be no, right. As a result of the cat, what happens is the fishes tend to be more on the left hand side than the right hand side. So, the equilibrium is skewed, meaning the stability of the products and the reactants is different because we have added some other factor, right, like the cat. So, if the new equilibrium condition is such that the left hand side tank is extremely attractive for the fishes because there is a cat sitting on the right hand side, then you will never achieve that 50-50 distribution, right. So, similar condition happens in the case of acids and bases. The stability of the end product and the stability of the starting molecules really determines which side is more favored. Now, let us look at the second question, which was about the concentration of NaOH. What will happen if we use a high concentration of NaOH, really high concentration? Will it be able to deprotonate? The answer is still no. Okay. Now, you can imagine that NaOH will react with that particular acetylene molecule, it will make that anion, but remember the backward reaction is equally favorable or rather more favorable. So, as soon as that anion is formed, it is going to react with water to go back to the starting material. So, eventually even if I will wait a really long time, I will never see a dominant product formation in this particular reaction, because the backward reaction is way faster than the forward reaction. As soon as the acetylene anion is formed, it is going to grab the proton and go back to the starting material. So, irrespective of how much more concentrated NaOH we take, we will never see that 50-50 formation here, right. Now, one thing that I must point out is that the K equilibrium we are talking about is the ratio of final concentration of products over reactants. Okay. This value is dependent on the final concentration. As the reaction happens, what is the final concentration, but it is independent of what concentration you started with, right. It is good to understand that we are talking about thermodynamic acidities here, which is the relative free energies of the reactants and products that determine the Ka values. Okay. This is in contrast to the kinetic acidity, wherein we were just talking about the reaction rates. So, now herein the stabilities of the products, the thermodynamic stabilities of the product will also play a role in figuring out what is the Keq of the reaction, right. Now, regarding the acid base reaction. So, acid base reactions are considered one of the fastest reactions in organic chemistry. For example, for a strong nucleophile or a base, it is very easy to abstract a proton in a deprotonation reaction than to perform a nucleophilic attack. So, when you mix two chemicals together, you are typically going to just quickly first see the acid base reaction happening if it is possible. Okay. Let us go back to our reaction here. So, NaOH was not successful in giving me a deprotonated form of the acetylene, right. That is because again if you look at the KEQ, it was going to close to -9. So, if I really need to form this product, which is the negatively charged ion here, which base should I use? So, the answer would be I need to use a base that will give me the overall KEQ for the reaction to be more than 1. So, let us take this particular example here. I am going to take the same starting molecule and then I am going to react it with NaNH2. So, instead of using NaOH, we are going to use NaNH2. What do I form? I form this plus NH3, right, because NaNH2 is nothing but Na plus NH2 minus, right. So, what do we have here? If I look at the KEQ for the reaction, it will be 10 to the power right pK, this pK is close to 35, this pK is close to 25. So, 35 minus 25, that is 10 to the power 10, right. So, if I use NaNH2 instead of NaOH in order to deprotonate acetylene, you get two different results, because in one case you are able to make the reaction go to the forward direction, in the other case as the earlier one, it will mainly remain as the reactant. Okay. So, now let us understand the origin of acidity. So, we can simply summarize it based on the golden rules or the 5-star principles that we had learnt in our very first class. So, what were the 5-star principles? The first one was that nature hates charges, right. So, that is something to know. Any kind of charged molecule, it is going to be very unstable and it is going to be difficult for us to stabilize that negative charge or a positive charge, right. And the second rule was octet rule rules, right. If you really think of these two rules here or the 5-star principles, they are talking about the stability of molecules, right. Octet rule governs stability to the corresponding element and nature hates charges because charges are unstable. So, we are talking about stability. So, when we really talk about acids and bases, let us write down one rule. So, the rule is stronger acids make stable conjugate bases. So, strong acids make stable conjugate bases. So, this particular rule is not a new rule, it is rather, as I said, derived from the first two things that we looked at. Now, let us look at an example. Let us take H3O plus, right, as the acid, and what will be its conjugate base? As H3O plus loses that proton, the conjugate base would be water, right. And now, let us take water. As water loses a proton, the conjugate base that will be formed will be hydroxide ion, right. Let us look at the stability of water versus hydroxide ion, right. Water being neutral, you can really find it in nature, extremely abundant form available in nature, whereas hydroxide ion, nature hates charges, it has a negative charge on it. So, you can easily say that this one is more stable, right. So, water is more stable, as a consequence of which H3O plus becomes a very strong acid, and that is also evident based on the pKa. So, you have -1 as the pKa of H3O plus, whereas 16 as the pKa of water, right. So, you can easily say that H3O plus is a stronger acid because its conjugate base, that is water, is much more stable as compared to water being a stronger acid, because water's conjugate base hydroxide ion is not very stable, right. One point that we need to ponder when we look at these pKa values, How much stronger is the hydronium ion H3O plus as compared to water when it comes to acidity, right. So, the reality is that it is 10 raised to 16 or rather 10 raised to 17 times stronger than water, right. So, it is not just a difference of 17 between -1 and 16. When we are really talking about acidity, remember we have to, this is pKa, we have to look at the Ka. So, it is 10 raised to 17 times stronger acid as compared to water when we are talking about acidity. Thus, if we really wish to understand acidity, we need to understand the stability of the conjugate base. So, as we saw that nature hates charges, thus we need to look at the charge stabilization. One of the things is that most of the conjugate bases are going to be charged, right. So, when we are looking at a conjugate base, the first question you should ask is the charge better stabilized in this particular conjugate base? Or sometimes if you have a neutral conjugate base, more often that particular compound turns to be a good acid, but we will also look at those examples. But the key question we have to always ask when we look at the stability of the conjugate base is that, is there any phenomena that is making this particular conjugate base more stable? So, I am going to go over examples and we are going to compare 2 or 3 different types of molecules. So, for example, here I have electronegativity of the atom bearing a charge. Okay. So, I am going to go over the criteria that make the conjugate base much more stable. Okay. So, or we can even call it phenomena that make conjugate base more stable. So, the first phenomena that we need to look at is the electronegativity of the atom bearing the negative charge. Right. So, what do I have? I am going to take an example of H2O versus ammonia versus CH4 as acids. If all of these 3 were going to behave as acids, what will be the conjugate bases? Water will form OH minus as the conjugate base, ammonia will form NH2 minus as the conjugate base, and CH4 will form CH3 minus as the conjugate base, right. So, the question is, what is the electronegativity of the atom bearing the negative charge? In the case of water, oxygen versus nitrogen versus carbon as we move in this series. If you really think about it, oxygen being more electronegative can hold on to that negative charge way better, and thus it will be much more stable than the nitrogen, and nitrogen will be much more stable than the carbon because of the difference in electronegativity, which is the ability of the particular element to hold on to the electrons, right. So, in this case, when we are talking about water versus ammonia versus methane, water is way better acid. So, we know that the pK of water is close to 16, pK of ammonia is close to 35, and for methane the pK is close to 50, right. So, that is also evident from their pKs. But the reason, the molecular reason why water is a better acid is because oxygen is able to hold on to the electrons way better because of electronegativity in the conjugate base. The second thing we are going to look at is the size of the atom that is holding the electrons. So, I am going to take an example of H2O versus H2S. So, water, as we know, will form OH minus as the conjugate base, and H2S will form SH minus as the conjugate base. Now, think of these 2 molecules, hydroxide ion and SH minus. In the case of H2S, the conjugate base has a much larger atom that is bearing the charge, right. So, sulfur is way bigger than oxygen. So, the negative charge can be spread on that sulfur in a much even manner as compared to having a strong concentrated charge in the case of oxygen, right. Nature hates charges, so being able to spread that one unit of negative charge all over the big sulfur molecule helps the H2S to really become a better acid, because the conjugate base SH minus is able to spread the charge and be more stable. So, if you really look at the pKa here, the pKa in this case would be 16, whereas H2S is around 10, way better acid, right. Similar phenomena is also seen in the case of HCl versus HBr versus HI. Again, if you look at the conjugate bases, it is Cl minus versus Br minus versus I minus. As we go down in the periodic table, what happens is you have the size goes on increasing. So, I minus is really huge as compared to Cl minus. I minus is better able to stabilize that negative charge by spreading it over a large surface area, and thus Hi will have a pKa close to minus 10, HBr will have close to minus 9, and HCl on the other hand will be close to minus 7, again indicating that Hi is a better acid than HCl. The third thing or the third criteria that we have to look at is the delocalization of charge. So, the delocalization of charge can happen in multiple ways. The first one that we are going to look at is resonance. Okay. So, now let us look at an example of a phenol versus cyclohexanol. If you look at both of these molecules, both of them have very similar structure, except in the cyclohexanol you are missing those double bonds, but you will see that the double bonds play a huge role in governing the acidity, right. So, the conjugate base, so these are my acids. What will the conjugate base look like? The conjugate base here will be phenoxide ion, and in this case the alkoxide ion, right. Now, which one is more stable between the phenoxide and the alkoxide? If you really see that particular oxygen here in phenoxide can distribute the negative charge on the carbon atoms by doing a resonance structure, right. So, you can spread these electrons or spread the negative charge such that you have all of these different negative structures, right. So, all of these are possible, whereas in the case of alkoxide ion, remember there are no pi bonds. So, the only bonds that you can really move in a resonance structure are the pi electrons or the lone pair electrons, especially this particular carbon has all the 4 bonds, sigma bonds. You cannot give electrons to it, right, such that there are no resonance structures here, right. In the first case, there are more resonance structures, but I have only drawn 2, but you can really draw up to 4 resonance structures. Now, what is this resonance structure helping in? So, you can imagine that the negative charge is like a hot vessel, right. I cannot hold the hot vessel all the time myself, right, effectively, as compared to if I have a couple of other people standing and I can say, okay, now you take this charge, now you take this charge, kind of like that we share the burden between all of us, right. This is not the exact analogy, because in resonance structure what you have is a resonance hybrid. So, we have gone over what resonance hybrids are, but imagine a situation very similar wherein the oxygen in phenoxide ion is able to share the load with multiple other carbon atoms, the load of bearing that negative charge, whereas in the case of alkoxide ion, that particular proton when it is lost, the oxygen has to bear the charge all on itself and is not really able to hold on to that charge very effectively, right. So, delocalization helps in forming more resonance structures, and more the number of resonance structures, more stable is the conjugate base, and as a result of which more stronger is the acid. Okay. So, the fourth phenomena that we are going to see, which is very often seen, is called as an inductive effect. So, in the case of inductive effect, let us take two examples. I have acetic acid and I have chloroacetic acid. Okay, so, one of the hydrogens on that particular methyl group is now replaced with a chlorine. Okay, so, now I have acetic acid, chloroacetic acid. I will also look at bromoacetic acid and fluoroacetic acid. Let us also look at iodoacetic acid. Right. Now, acetic acid had a pK of close to 4.76, right, or 5, but let us look at the exact pKs in this particular example. Chloroacetic acid is going to have a pK of close to 2.86, bromoacetic acid will be close to 2.9, fluoro is 2.59 and iodo is 3.18. So, what does this trend really tell you? If you look at this, fluorine is electronegative, a lot more electronegative as compared to chlorine. Chlorine is more electronegative than bromine, bromine is more electronegative than iodine, and iodine is really more electronegative than that hydrogen, right. So, as we go on adding an electronegative group at the alpha position, what we see is that the acidity goes on increasing as the electronegativity of that element goes on increasing, right. So, if you think about it, let us look at acetic acid and its conjugate base. So, in the case of acetic acid, the conjugate base is stabilized by resonance, right. Now, if I change this particular hydrogen to a chlorine, okay, what happens is that the negative charge on that oxygen is getting, of course, resonance stabilized, but also chlorine being more electronegative is going to pull electrons via something called as an inductive effect. So, inductive effect is a through bond effect, meaning you can pull electrons through sigma bonds, and as a result of which the negative charge gets spread on the entire molecule. So, in fact, you can refer to this next diagram which talks about how inductively chlorine or fluorine are being able to pull electrons away from that acetate ion such that it spreads evenly on the entire molecule. And as a result of which, what happens is you can make the acetate ion, the corresponding acetate ion, way more stable if you have an electronegative atom present. Now, fluorine being more electronegative pulls the electrons way better than iodine, for example. So, fluorine makes the pK go down to 2.59, meaning fluoroacetic acid is going to be much more acidic than iodoacetic acid, which has a pK of 3.18. So, all of these criteria or all of these phenomena are very typically seen, but there are even more different phenomena that may give rise to difference in acidity of two molecules. We are going to look at these phenomena in the next class, and till then what you can do is you can look at the pK chart and figure out why the pK of a particular compound is what it is written. So, for example, between ketone and acetic acid, why does the pK change? Why is acetic acid way more acidic as compared to ketone? So, you can think about all of these different combinations in your pK chart and figure out a reason why the acidity of a particular molecule is higher or lower. Okay? Thank you.